great.
Okay. Yeah, so we've again, my name's Russell Berry with Intake Screens. And I've put together a slideshow with some pictures and videos just to kind of give you a history of our company and what we do and some of our projects that we've worked on. So most of our screens, we build self-cleaning intake screens, mostly all based around fish protection. And so all of this started back in Nebraska. My dad worked on a ranch in the 70s, and he was pumping water out of a sandy, shallow river there, and he was getting leaves and sticks and pine needles and everything in his irrigation system. And so he built a self-cleaning intake screen for his pump, just solely for filtration to keep his irrigation system clean. And then through the 80s, he had a business in Nebraska building really lightweight water backwash screens, intake screens, all based around irrigation and filtration. In 1990, he sold his company to Lacos in Fresno, California. And so we moved to Fresno. And also in the early 90s is when the fish screens started to become of age because they had protected species of fish. And so they took one of these lightweight water drive screens and scaled it up, built a really big lightweight water drive screen and put it in the Sacramento River up here by Knight's Landing. So that installation was in 93. But from that experience, he learned that there was a need for a more industrial grade screen that was based around fish protection, maybe more than irrigation or filtration. The screens we build, we primarily use wedge wire screen material. Wedge wire is a really nice screen material. You'll see a whole bunch of it around here, but it's a triangle shaped wire, and so the slot actually gets larger, so that any flow, the maximum flow velocity is right here at the slot, and then it slows down as it goes through the slot, and it keeps any material from clogging up that slot, that opening slot. But then we also add a brush cleaning system. So the exterior brush pokes through the wedge wire screen material to wipe it off, and then the internal brush rotates and extrudes through the screen to keep anything from growing inside the screen. And so it's a really thorough cleaning system. And so we adapt this cleaning method to screens all different shapes and sizes. We also build a cone screen. And so picture this over your bathtub drain. Water flows through it, and then the brushes sweep around and wipe it off. We primarily use in really shallow water environments. So where water depth is an issue, we can get a lot of screens submerged really low. So creeks, rivers, and then we started building these in the late 90s. There's a bunch of projects that we built screens for on Grizzly Island in a tidal estuary marshland. We rotate these screen cylinders by either with a hydraulic drive. So we have a motor in the screen that rotates the cleaning system. So we can do that with a hydraulic drive. We have an electric drive system. So this is just a submersible pump motor that's coupled to a high reduction gearbox. And this electric drive really opened the door for us to operate a screen that's maybe further offshore. So we can go a mile offshore and put a screen out in the bottom of a lake or something and have the controls back on shore. And then we have this turbine drive system, which is here on a couple of these screens here in the yard. And this just uses the energy of the water going through the screen to propel it to spin the turbine, which is coupled to a high reduction gearbox. And this was originally developed because down here in the Delta, there's a lot of sites where they're just siphons, and so there is no power available. And so we'd go out and look at this intake, and maybe it's a 14 or 16 inch pipe there's no power available, and so we could put together this turbine drive screen and screen that intake without having to add any other power or anything like that, and it just uses the energy of the water to run the cleaning system. And then when every site's different, all site conditions are different, and it's primarily the fish screen criteria that drives the design, which is going to be the slot size and the uniform velocity. But then there's all the other site conditions, head loss and ice and mussels, and so we'll get into that. So the slot size, most screens in California are designed around a slot opening of 1.75 millimeter, which is about a 1/16 of an inch. In Texas, we built some screens that have 1/4 inch openings or 1/8 inch openings, and in New York, screens in New York we've built are 0.75 millimeter openings, so they're much more conservative screen criteria in New York. And it varies from region, and it varies for what type of fish are present and what they're trying to protect. Uniform velocities is a big part of it, because we can't have a screen that has real high velocities going through it, sucking everything up against the screen or through the slot. So that's what this suction pipe manifold is. You see on all the screens, you can see through the screens out there, and that's just a baffle system to restrict the flow near the intake and encourage more flow further away from the intake. And it's just an effort to evenly distribute the flow across the screen surface. And then anytime we have multiple screens on a manifold, then there's always an effort to balance the flow across multiple screens. And so in this particular example, it's hard to tell what that is because it's a foreign object, but you'll see it in some other pictures that come up. But this is 16 screens that are all hooked together on a manifold, and we built this big array of screens so that the flow path from the center of this intake out to each screen is the same distance, and so in theory should draw the same amount of water. And so we were able to show that in a CFD model, and then that's what we used to design that system, which we'll see more in a little bit. Large debris, this is always an issue. We're always building screens that are out in the waterway, and so traditionally you'll see a lot of maybe power plant intakes. Screens are designed to remove debris out of the water. They're keeping their screen clean and they're removing the debris, and it's going into a dumpster. And with fish protection, it's better to put the screens out in the water source and have low velocities and leave the fish and leave the debris in the water and not handle it, not try to remove it. And so a lot of our screens are out in the waterway, and so then consequently you deal with trees and branches and boats and everything that would come downstream. And then ice is a huge obstacle in some regions, and so this is up in Montana. There's a big river that it freezes over and then it thaws in the spring, and that ice comes downstream, and it's the size of cars that come crashing down the river. And so this screen system is able to be raised up out of the water when they have the ice flows. And then this is the other picture is the city of Bend, Oregon, and they have a small creek they're taking water out of that gets ice, kind of an ice slushy or a frazzle ice, and so they have a heated water jetting system around the screens to keep ice from forming around the screens. And so that's always a design parameter that we work around in where it's relevant. Mussels, there's certain watersheds across the U.S. that are being infected with mussels. This is the Colorado River. So this is an anti-fouling coating that's been applied that seems to be effective to keep mussels from growing on it. And then our brush system is really effective at keeping mussels from accumulating or growing on or in the screen. And that's really where that internal brush does a really good job of keeping mussels from growing in the screen. And silt and algae, This is the screen that's just right down here in Clarksburg, and this is very typical of Sacramento River. And I'd say Sacramento River mostly it has a lot of sediment, a lot of silts moving downstream, and so you get waves of mud that settle on any surface. And so what you'll see, like these screens that are here in the shop, the floor of the screen's flat, and we try to minimize any surfaces that can accumulate mud. And then the cylinder rotating keeps mud from accumulating in or inside the screen. Hydroids, this is estuary seawater environments. We get these mussels and hydroids growing, and again, this is we have anti-fouling coatings and aggressive brush system to keep that from growing on the screens. And then low water is or trying to get a water body that's deep enough to fully submerge a screen. We're always designing around what's the maximum flow rate, and then what is the water depth, and that determines the size and how big or how many screens we might need to have to get enough screen surface submerged to have the low velocities. And so this is just a picture of this is up in Red Bluff, and these screens are 14 foot in diameter, but they can divert water out of with just 3 or 4 feet of water depth. And the brushes sweep around the exterior of that. And then this is just a vertically oriented cylinder screen, and we use that because it has the internal brush, and and the internal brush is really good at keeping sand and rocks, and that was an issue at that particular site. And then this is a really common scene on the Sacramento River. This is right by Knight's Landing, where you have this high water level fluctuation. So we would design this system around the screen being fully submerged at low summer flows, but then has the ability to be raised up out of the water during the high runoff in the wintertime. And then there's sites where there's no power available, so we can adapt our cleaning system to run off of solar or the turbine drive. And then last but not least, every site's different, and the method of installation or construction is always different. And so we'll adapt the screen and maybe the structure that it's being mounted on to go along with the contractor or the engineers that are designing how it's going to be installed. So sometimes they'll put in cofferdams and dam off a site, and dewater and be normal construction activity, and then sometimes it's all installed with divers underwater. And so with that, we can stand up a complete assembly, completely assemble it, put all the nuts and bolts in it, test run everything, and then break it down and pack it up and more or less just ship out a kit that would be reassembled or installed on the site. And I put together just a couple project examples, and these are large projects in chronological order. And so in 2005, we did 2005, and then it was installed in 2006. We built the Reclamation District 999 intake over here in Clarksburg. And then 2010 and 11, we installed an intake dam in Montana. And then 2016, we built Cayuga in New York. And so I'll go through pictures of those sites. So this is just about 4.5 miles away on the Sacramento River. This is an existing 42-inch siphon. When the water's high, they can divert up to 100 CFS. The screens are designed for 0.2 feet per second approach velocity. And so to get that much screen area, we doubled up 2 T screens on a retractable system. So those screens can be slid down the rail over the intake. And then in the wintertime, when it's not irrigation system, they can pull those screens up and let them sit up out of the water, so they're not growing algae or anything on them, and there's no corrosion going on. So there's just a couple of the pictures when we're designing it and in operation. And this is intake dam. So this is a 1,450 CFS diversion on the Yellowstone River in Montana. This is designed around 0.4 feet per second approach velocity, So this site here in to have that flow rate here in the Delta, it would be twice the size of that. So that would be like equivalent of a 2,900 gallon CFS diversion. So this is the Yellowstone River. Yellowstone River is a wild, untamed river. There's no dams upstream of this, and so they'll get wildfires, thunderstorm, and then they just get this slug of debris that comes down, and it sits in a real low pool in the summertime. The water is screened, going through the screens and then through that head works down the irrigation canal. So this is just a picture of it in the summertime. There's real low flows, and then the wintertime it gets this big ice runoff, and so they can pull all the screens up, and that all rushes through there, scours out the bottom. And then this is this Cayuga Lake intake. These are all vertically oriented screens. These are 7-foot diameter, about 10 feet tall. There's 16 of them arranged on a single 8-foot diameter pipe. And this is an existing intake that we retrofitted because they had new fish screen rules and criteria that came out. And so we retrofitted this intake in 2016. It's about 50 feet deep. The inside of all the pipe manifolds coated with anti-fouling coating to keep mussels from growing in there. They have a real bad mussel infestation in this lake. And then the existing power plant, they couldn't withstand any more than 3 inches of head loss, and so everything is really big, just so they have real low velocities going through the piping manifold. And this is I got to go out and dive on it this last June. So this has been installed for 3.5 years. There's the mussel accumulation on the exterior brush arm. The screen's clean. Every surface has about 3 or 4 inches of mussels growing on it. And these screens have been coming on and running. They run for a minute forward, and then they might run a minute reverse, and then they shut off for an hour. And then so they've been cycling, running 24 every hour, 24 times a day for the last 3.5 years. And then this is a shot inside of the manifold, so we can open up a big door and then go inside that pipe. So the inside's coated with this blue anti-fouling coating. It's really effective at keeping mussels from growing inside the pipe. And then the inside of the stainless steel screens is coated with this copper coating, which you see on these screens. And that keeps mussels from growing inside of the screen. And then the brushing system is effective at keeping anything from growing or accumulating on the actual wedge wire screen material itself.
So with those brushes,
yes,
there's a bunch of mussels growing out.
Yes.
Do they ever extend far out?
Well, that's what I wanted to go see, because we installed all this, and I was like, I want to go check this out, So I went and dove on it just last month, and this is what we found. So it looks like the internal brush, it gets a little bit of mussels growing like in the brush, but I think that they get disturbed or broke off when they come into contact with the wedge wire.
And did you have to replace that coating?
We haven't yet. Time will tell.
So just wait. You're not anticipating any particular time?
It looked. Everything looked really good, and that's what I was. But anti-fouling coating, by nature, it's either sloughing off or it's kind of degrading over time. So you would think any kind of anti-fouling coating wouldn't be like an indefinite solution. It's going to become less effective over time. Sometimes you see like you'll get like a calcium buildup or something on a coating, and then other stuff can grow on top of that. And these are oriented vertically because they're in a lake, and so any work that would ever be done to them would be from above. And so if you wanted to take a brush out, a diver would, they could pull it straight up. And so that's why everything was mounted vertically. And then this is just a video of a screen up on the Columbia River in they had put in 20 screens without any cleaning system. They were just passive screens, and those became buried. And so then we got a job to go out and retrofit that intake. And so then maybe 2 years after we installed it, I got a chance to go out and dive on it and check it out. So it's beautiful. It's down there, runs a couple of times a day. There's all this weedy material. There is a water backwash system on this screen. So they're pumping water up a hill, and they have all this back pressure. So they have a surge chamber. So we tapped into that surge chamber and ran it back down. So when the screens run, there's a valve opens, water jets out. And so that's what you see. You can get this ball of grass and stuff, and it'll hit this jet of water, and it kind of blows it off away from the screens. This is in a river, but it's kind of in like a back eddy on the river, so there's not a lot of sweeping flow. And so there's this supplemental jetting system to help move any debris downstream. To the screen? No. You can you can see like the weed right there, like kind of tumbling, falling down the screen. And so generally screen systems are designed around the maximum flow rate, and then you even round up a little more off of that. And so they're generally pretty conservatively designed. And if you went out and wanted to try to like feel flow on the screen, you can rarely feel it. Or you can take like a trash bag or some plastic or something and put it on there, it probably like float away because the velocities are low enough. If you ever, I always say that we build all this stuff for cleaning all this, but really the easiest way to make a screen work really well is make it too big. Just keep the velocities low. And here in the Delta with the criteria, it kind of does that for you because you basically you have that 0.2 feet per second approach velocity. So for every cubic foot of water, we have 5 square feet of screen surface. So you get, yes?
So Russell, have you ever built intakes as big as they want you to build out here? And what is that? Can you remind us how big they are? And then is there any type of fish screen that actually is like 100%, no fish loss whatsoever? Does that exist in the world?
Okay, so I'm supposed to repeat the question. So the question is, have we built a screen as large as they're talking about building down here for the Delta Conveyance Project? And do fish screens exclude 100% of fish? So just for an example, the Delta Conveyance screens are very similar to these screens that are here in the shop and up on the stand. The difference being they'd be about a foot larger in both directions. So it'd be 8 foot diameter. These are about 7 foot diameter. That would be about 8 foot diameter screen, and I think they're a foot longer than what these screens are. And we have built screens that scale. But every site's different. So what we built, out of another project is maybe relevant or maybe not relevant to, these conditions. But they're very similar.
And how many of those per intake?
We have right now that intake dam project is 12 screens lined up on a wall. This project's it has 6 right now, and then they're building another 4 in the future. So it'll have 10 on it. And then as far as excluding fish, it's hard to know. Most of the California criteria is all based on fish that are able to swim, whereas when we go to New York, they're looking at eggs and larvae. And so I don't really know. John might be able to answer that a little bit better.
Yeah, I think, so I spent a lot of time looking at different technologies that can protect fish. And you have a lot of systems like Russell talked about that will collect fish and convey them, and you're immediately handling them and causing mortality. And so wedge wire screens leave fish in the water, have a very small slot size and a low through screen or approach velocity, and so you have much less probability of even interacting with the fish. They can swim up against it and move. Even fish larvae and eggs that aren't particularly motile can come up against that screen, and you have a sweeping flow that will take them off. So it's hard to say that there's any technology out there that is 100% protective. But if you want to build one for a particular site, your starting point would be a cylindrical wedge wire screen, and you would design it to really maximize that fish protection. So you'd play with the approach velocity and the slot velocity to achieve what you need to. And so in California, we have these federally protected salmonids. You can't handle them, you can't disturb them, touch them, because that's take under ESA. And so you quickly go to this kind of technology where you're withdrawing water, but you're not impacting those fish, you're not handling them.
Okay, thank you. And to be clear, so you said it would be 10 of those per intake on the Delta?
Oh, no, it'd be,
30 of those?
I think it's 30. I don't know. I've seen lots of different layouts, but Phil would know.
You know, the 3,000 CFS intakes, there'd be 30 of those big ones. On the 1500s, some of the options on 1500, so they're each 100 CFS.
And I'm sorry, Russell, how long are those each? You said
Those are 100 inches long.
okay.
Yep.
And it'd be a little bit bigger.
Yes, I think they have them laid out right now, maybe.
Total length and
It's 100, 200, and then 7 foot between them, so 280 or 90 inches.
ours are 30 feet, Anna. These are probably.
I think these are about 28.
Okay.
Yeah.
So
Yeah.
30 times 30?
Yeah.
Okay.
Yeah. So if you some of the stuff I showed you in the meeting, the total structure length is 964 feet.
964
The
feet.
screen length is slightly smaller. There's a foot. You put a foot between them. That's something that can be verified during final design. We might be able to skinny that up a little bit, but right now we got a foot between them, and then there's a little bit of room on the ends of the concrete structure because there's stuff inside it that we have to be able to get out, and that's on the ends.
Okay. So a little bit longer than 900.
Yeah, and that's actually shorter than the vertical plate ones that we've also
Right.
been talking about.
Right.
And that yes, sir.
What's the cost of a fish ring like that?
What is the cost? Depends on all the bells and whistles that go into it, and so it's hard to say, how much. I think this is this project that we're building for the city of Houston is about a $4 million project, and it consists of 6 of these screens and 10 of the track systems that are stood up out here because they're going to expand on it in the future. So they have 4 spares, and then the controls.
So that's roughly 700,000 per unit.
No, it's 250, I think.
Oh,
What is that?
56 of them, all right, at 4 million.
Yeah. So call it 3 without the spare track. So 3. So it's about $500,000, like for that assembly that stood up out there in the yard.
And the screen.
Yeah, for the screen and the track system that we have there.
We're not using that same system. It would be slightly different for what we're going to do. We can talk about that.
Yep. So that's all my pictures. So let's go out. We can run one of these screens down, and then we can talk about how it works a little bit. So just to describe what you're looking at here, this is going to be mounted vertically on a pump station, and then coming out the back is a 6-foot diameter pipe that would be tied into a wet well where they'd have a pump. And so this particular pump station, there's 6 of these being installed, and then with 4 in the future. So there's this large pump station out in the lake that these are going to be lined up, more basically 5 on each side. And so an operator can go out and lower this screen down over the intake or raise it for inspection or maintenance. Yes, sir.
Into the shed.
I see.
What's the approximate weight of an assembly like that?
That's about, I think it's 11,000 pounds.
That's all?
Yep. No, that assembly, no, this is a screen. The track is 17,000. So total, we're talking about close to 30,000 pounds.
Well, this may be a dumb question, but when you raise it, when you have water in it,
Well, if you step over here, sorry to mess up your video. So we build the bottom of this flat, so when we raise it up, everything can run out.
Draining.
Yep.
Okay.
And then generally we would build a gate in this particular site doesn't, but a lot of times we'll build a gate in the track behind this, so the opening can be closed and then the screen raised.
I got you.
And then
The
they,
water be pouring out of the screen anyway. wouldn't
yeah, it just drains, but it'll have, like, a lot of times any flat surface might have like this much mud all over it, you know. And so we build this so it kind of drains out. You'll see like all these are opened up so that mud doesn't set in the corners and it drains out. And then that is just the internal suction pipe to evenly distribute the flow, and then it also supports the end of the drive assembly. And then this is the internal brush in the bottom of it.
So this triangular wire, I'm surprised that the spaces are that wide.
Well, and this is Texas. So everything's bigger in Texas.
You say so.
Yeah. Over there on those two cylinders, you'll see that they're really tight.
Okay.
And that project's going to Virginia. And so they have a criteria with 1 millimeter slot openings.
They want to protect their striped back.
Yeah.
so the track or the power for running it up and down.
Yes.
That's electrical?
That's hooked on the winch up there, so that thing's rolling. So it's hooked to those cables that pull it up and down. Mm-hmm. There is a cable carrier system, so that screen has cables and it's pulling it down. That's what that big stainless steel box is on the side right there. Mm-hmm. And so it's pulling all its cables with it, pulling them down, and then when it rolls up, it pushes them up in that box. Mm-hmm. And if you walk around the other side, you can see that. I'm going to rotate. Yeah, John, go ahead and rotate the screens, and we'll walk over and look at the screens
rotating. What
rotating.
did you use for power where you said to replace it, they didn't have power?
I'll show you that, these turbine drive assemblies, but we'll show you that in a second.
So is this the typical, each one would do this?
Yes.
And do they run 24 hours a day?
No. So a typical cleaning cycle would be that the screen rotates like this for a minute forward and then a minute reverse, and then it shuts off. And so it might shut off for 6 hours or 12 hours, whatever it's set to. And so in an area where there's a lot of sweeping flow, there's not debris like accumulating on the screen. It's mostly being swept by, and so we're just keeping the algae from growing on it.
Oh, okay.
If we had this in like the end of a canal or in like a pond or something where the water's not moving, then they have to run a lot more often, because it might run and wipe the debris off, but the debris goes like this far away and then it's going to come right back, and so they have to run all the time. And so in a river environment, it really can just run. Probably in the Sacramento River, we have a lot of sites, they just run 2 times a day. And it's just wiping the algae off, and then it'll shut off for 12 hours, and it'll come on and run through another clean cycle.
Required by regulation
To be able to run complete cleaning in 5 minutes, and they have to be able to run continuously.
Yeah. So so the regulations require a ability to clean,
Right.
Okay.
You don't have to do it.
but the reality of it is as long as the screen's clean. And so there's usually it varies from site to site, but our controls are always based on a timer. So an operator is going to set that the screen runs, every hour, every 6 hours. Say, 4 hours into that 6-hour cleaning cycle, there's a big, inflatable raft that comes downstream and it wraps around the screen, or, it gets a big slug of something that plugs it up. Then there would be a differential, and that would activate a cleaning cycle as well.
So there's not a sensor actually on it. This is all based upon human operation. judgment?
Well, no, that's what I'm saying. There would be a differential sensor that would be in the background, but we wouldn't want to rely on a differential to happen to activate a clean cycle. We'd want to have the cleaning cycles happen on a regular time schedule, just like set to every hour or every 6 hours, whatever it might be. And then if something happened, where it needed to clean more frequently, then you would see a differential, and it would go through a cleaning cycle.
So in our design, we include what we call a hardwired. If the drop ever got too much and the screen wasn't fixing it, it would automatically shut off. It would go straight to the power source and cut it off.
Okay.
Is that cycle consistent throughout the year, or does it differ with migratory patterns or anything like that?
The worst event is the first big runoff. Where everything, like when it rains in October, November this year. That's usually when the water's the dirtiest. But yeah, it can be adjusted per seasons or as needed. But
so a couple other things I wanted to point out. When Russell talked about the garbage bag sticking to it, we're required to have twice as much flow flowing past them as we're ever pulling in. So in order to get up to the maximum capacity, there's going to be a lot of flow in the river. So it'll be a pretty good sweeping flow. So the really slow flow in, like he mentioned, it's probably even more of a case for the Delta screens. Stuff will just blow by.
yeah.
The other thing I wanted to point out is this system, it's possible we could end up with a system like this. Probably not with 60 of them, probably not individual winches like this. It'd probably be a movable crane that would move them up and down, but the system we're looking at now doesn't use this rail because you notice the pipe is fixed at the bottom. We want the ability to be able to set the screen at a different elevation over time, given our resiliency goals for sea level rise and that kind of thing. If the conditions of the river change, we may have to move up a little bit.
Mm-hmm.
So it's a different system that would be hoisted up and down in a guide rail. It'll be real similar.
It's real similar, but there's more if you're building 60, there's more efficient ways of using less components than what we have displayed here. This is an operator can go up and hit a button and the thing comes up out of the water. Whereas what they're talking about is they might have a crane that could be used on the whole line. So there might just be one or two cranes that could be used for the entire length of screens. So it reduces a lot of components. What's that?
There are a lot more flow rate than we're talking to because they're pointing.
Yeah, so these screens probably, these are sized for 0.5 slot velocity. So it's a point, I'm not sure because the slot opening is different. They're in a...
Because ours only have a 5-foot pipe behind them.
Yes. Yeah, so, and that's why we can reduce the overall length of the assembly because that center manifold is narrower than it is here because we aren't handling as much water through each individual screen. Think about here, compared to like a flat plate screen, if you took this wedge wire cylinder and unrolled it, both of them, it would be the height of that container, that shipping container, and it'd be about 5 feet longer. And so that's a good visual to compare like a cylinder screen to a large flat plate screen.
Our flat plates are, at intake 2 they'd be 12, at intake 5 they're 15, and at intake 3 they're 17 and a half feet tall. So this is 7, right?
Yes.
So the smallest flat plate is practically double in height, and the larger ones are almost 3 times. So the flat plates, they're longer. So that is the thing that fisheries folks like, though, is the nice flat surface rather than having the tees sticking out in the water. That's the big difference. We expect these structures to be comparable in cost, so it's not a cost issue. And the DCO is evaluating with the agencies which one they prefer to use. And I've been showing you guys both all along.
Do you build any kind of screen? Flat?
We do. We recently built a flat panel screen, mostly because it was part of another system that we were already building some screens for. But traditionally, when we're looking at sites and laying out a structure and figuring out the best way to do it, we mostly always come back to a cylinder screen, just because it's really efficient. Our cleaning system, to clean this, we have a motor. It's directly coupled to the cylinder, and so when that motor rotates, the output shaft's going like 2 RPM. It's going real slow. It's direct drive, and then it just rubs against these brushes, and it can go forward for a minute, it goes reverse for a minute. It's brushing the inside and the outside, so there's a lot of good things about that. Whereas with a flat plate screen, you have more of this linear brushing system, and so it's a little more complex cleaning system, and usually it only cleans the outside of the screen. And so we have built flat plate screens, but we usually, when we're involved in designing or laying out the options, we usually come to this conclusion, except for the cone screens, and that's just because we can get a lot of screen surface submerged low with a cone screen.
The one that looks like an octopus?
It's like a little space shuttle. Yeah. Yep.
We're not using those because of the flow rates we're talking about, they'd be so big.
They'd be massive. Yeah, it's not an efficient way. The cylinder screens is the most efficient way of getting a lot of screen surface in an area.
Actually, there's one over there, isn't there?
Yeah, we have one right here in the driveway. And feel free to walk around and look at stuff. And there's a propeller drive screen over here. You can spin the propeller and kind of feel how that system works. You can look inside of these. None of these are turned on. And then this screen that's set up over here, we just got done, welding all that this last week. And so I was like, well, we got people coming over. Let's get it set outside. And what that is that's a screen with a finer slot size. It's 1 millimeter slot openings, and so that's a little bit tighter on the wedge wire.
Is there a water jet on there?
There is. They're pumping water. It's in a pond, and so I feel like the bottom's going to silt up underneath of it, and they're pumping water up a hill, and so they're going to be able to drain that pipeline, and then we plumbed it back to that, so it can just jet out underneath the screen. And just clean underneath of it whenever they turn the pumps off or want to drain the line.
We have jetting in our structures. It's similar to what he's talking about.
Yeah.
But it's not built in.
Yeah. And I was going to say, we've recently added a submersible pump in the screen, and so we'll just have it coupled right here in the back. It's just like the same motor as our drive units. It's just the third motor, and then we can plumb that to a spray bar on the brushes or blowing down. And so we're doing that on a project for ice. We're going to have a pump in the screen, and it's going to blow water out towards the surface to create a boil to keep ice from forming along the wall. And the beauty of that is there's no plumbing. It's just the electrical cable that's going down there anyway. But that could be done, down underneath the screen from the inside out, to induce flow.
Are these copper coatings allowed in California?
No.
Yeah, I didn't think so.
No. Yeah.
I don't know why, because they work the best.
They work really well, but Texas and New York is where we've had this type of coating.
Radials, they're a set of, all right, so these things are attached to a structure, and the structure these pipes. The pipes have control gates on them. And so by pumping 40 miles away, they induce a drop between the river and the sedimentation basins behind them, right? So we modulate the gates, and we have flow meters on every screen, so that the flow stays within either the permitted or the desired amount. The desired amount is less than 50. So the gates, once
downstream, let's say they start pumping and the gates control the flow through each of them.
So Phil, there is a gate behind each screen.
There's actually 3.
There's 3 gates behind each, but
One right behind the screen.
so and is that what you're going to use to? So you can you're going to have a gate and a flow meter, or
Probably going to use the furthest downstream gate to modulate. We got all these gates for a variety of reasons. For dewatering, so she wants me to take my mask off. So we have the gates for a variety of reasons. We have to be able to isolate the facility for flood protection and for maintenance. So that's what the main gate right behind the screen's for, is just to be able to isolate the piping. When you pull up the screen, we also have a drop-in gate so that fish can't go through when the screen's not in, right? And then it goes through the levee, and at the back of the levee there's a structure right before it goes into the sedimentation basins. And that's also for isolation, but one of those gates in there, on the downstream end, it's like 50 feet, or no, it's like 100 feet away. That will control the flow through that pipe, which controls the flow that comes in through the screen.
So on the intake, so the flow from the intake should never be stronger than the natural flow. I thought I heard you guys say that earlier.
So the way the regulations work is there's rules about what they call bypass flows. That's the flows that sweep past, right? The sweeping flow versus the flow you take in. And there always has to be twice as much velocity, and they do that by flow because it's flow is proportional to velocity. So there has to always be twice as much flowing past as you're bringing in. So let's say we have a 3,000 CFS intake. The river upstream would need to have 9,000 CFS in it. Now, these rules are being worked on by DCO. I'm giving you general, I don't know if it's exactly twice. A lot of places it's only 1 time, right? So I got to be careful with that. I don't think those actual rules have been worked out with the agencies, but in general, there's a rule. So let's say it's 2 times. So there'd have to be 9,000 going by to take 3,000 out. And when Russell talked about this 0.2 feet per second, I want to put that in perspective. If you were out strolling around in a park, you're probably walking at 2 feet per second. So we're talking about the flow coming through the screen at about 1/10 of the speed we've been strolling around here. So it's really coming in quite slow, and that's why he said like a garbage bag may not even stick to it.
Yeah.
The sweeping velocity will take it past.
yeah. And that what's that?
Times 60 then.
Yeah, but that's why the structure is so large, is because of that really conservative approach velocity. Is that almost it doubles the size of the intake compared to like something you would build in Oregon or Washington.
Well, or even further upriver.
Yeah, it's a third larger than past the I Street Bridge.
So like the Freeport's a 0.2 screen, but the city of Sacramento's big boat, that's a 0.33. So it's more than 1.5 times faster coming in because there's no delta smelt. At least at the time they built that. Today that would probably be a 0.2 as well. But the one we have up at Knight's Landing for Natomas, those are 0.33 screens. That's for salmonids. And then 0.2 is for delta smelt and other juvenile delta species, sturgeon and other things like that.
Did you build Freeport?
No.
Freeport's flat plates.
I'm already impressed with the engineering and how these screens work,
We all are.
but I'm kind of thinking to myself, as good as these things are, what good are they if the fish get past here and get sucked down the Old and Middle River to the pumps where Clifton Court isn't screened?
Well, Clifton Court is a different issue. I don't really know what to tell you about that because it's not part of our project. I understand what you're saying now. It's clearly an issue. Now, the idea would be that when we're running this, maybe they're not running that, but that's an issue that has to be vetted through people.
So who's working on
this
that?
has come up at the SEC quite a few times. That's just something you have to deal with DWR on.
Who's working on it?
I don't know. I
Is
know
anybody
somebody
working
is.
on it?
It's not part of the Delta Conveyance project. Our project bypasses all of that.
What's the, maybe you just talked about this and I may have missed it, sorry if so. But let's just say you got 9,000 CFS coming down, you're converting 3. What's the impact for velocity or anything further downstream? Since you're, let's just say you're taking out a third of the flow, what happens to the flow just downstream? Anything in particular?
I don't know that. I think
Not
the DCO is in the process of evaluating that, and I think it's part of their EIR analysis. I don't really know.
Yeah, thanks. Just when you've got a length of these things going on here, what ability do you have for any mitigation like on site? I mean, can you put like big trees in boxes along the way for riparian habitat, shade, anything like that? Or is this, when you have these in, you have to have it clean and industrial?
You know, a lot of sites that we work on, we're retrofitting like an old pump structure. So if you went over and looked at the 999 facility, it's a 42-inch pipe going down the levee with riprap, and there's an oak tree right there beside it, you know, and the screen like squeaks past it without, you know, it's not in the way, but it's close. And so in theory, you could build a facility like that, but I think on something of this scale, it is more of an industrial facility because it's, you know, it's a big civil works project and intake. And so they have. I mean, Phil can tell you all about it.
Well, I don't know what they're planning for stream bank restoration. That's when the EIR evaluates what the structure does to the riverbank, then they propose mitigations. And I don't know what those are. Now, I do know that all the places we're looking to put them, for the most part, don't really have a lot of. There's bushes. Not really any trees per se. At least on the riverbank. And you know, there's a reason for that. It's that all these places are U.S. Army Corps of Engineers regulated levees. They don't really want trees growing.
Yeah. From our perspective, we wouldn't care if there was a tree between every screen, but we're just building this widget, you know, and how it plays into the levee system is probably a bigger deal, you know, as far as what kind of vegetation's on the levee. Then, well, thank you. It's always talking about screens is one of my favorites, or screens in general is what I do. So it's always nice when I have a collective audience to talk about screens too.
How long would it take you to build 30 of these?
I think we're building close to 30 screens this year. Not this size, but
I mean, you're not gonna
collectively.